Hi everyone, I'm here to talk about upscalers, but before I do, I should probably start by introducing myself. My name is, technical difficulties again. My name is Dominic, and I am a game and middleware developer at the Naked Dev. And before you ask, no, we're not always naked at the Naked Dev. We are actually firm believers of wearing clothing, but we also really believe at being open and transparent about the technologies that we create. A few months ago, I've been asked to give this talk at GDC, but because of the very great hospitality in the United States currently, I decided to also give this talk here at the Netherlands, so you could all also enjoy the talk. Over the past few years, we've been creating upscaler integrations for Unity, like FSR3, DLSS, XeSS, and a few more mobile-oriented ones, like SGSR and ARM ASR. Originally, we created these integrations for our own games, in-house developed games, but we did notice that it was a big ask in the Unity game development community to also port these assets to everyone else. So we decided to start porting this asset to the Unity Asset Store. But what is upscaling exactly? Well, when you start a game for the first time, it generally boots up at the native resolution of your monitor. But if you have older hardware or a lower spec GPU, you won't get a 60 frames per second output. And in this case, it can help to lower the resolution of your game to get a performance benefit. And it will look like something like this. Wait, no, it shouldn't look like this, actually. What a lot of people don't know is that when you lower the rendering resolution of your game, it should actually look like this. But there's another technique involved called bilinear upsampling to stretch out all the pixels that are being rendered over the entire monitor, leaving you with a native output, making it look like this. A little bit blurry, but at least you can enjoy the game at the full resolution. Now, the difference between upsampling and upscaling is that where upsampling only stretches out these pixels, upscaling also makes it, or tries to make it look good, almost like a native resolution output. Now, this upscaling isn't done for free. There's a render time cost, but in many cases, this cost is actually lower than the performance benefit you can gain by lowering the rendering resolution, meaning that in most scenarios, you get a great performance boost, which is great, of course. If we look at a real-world example of our in-house developed game, City of Springs, as you can see, when we render the game at a native resolution of 4K on a medium-spec PC, you can see that the rendering time is about 17 milliseconds, which is quite a bummer, because it's longer than the magic 16.6 milliseconds needed to get a frame rate of 60 frames per second. Then, when we lower the rendering resolution, you see a drastic decrease in render time, like on quality setting, where we lower the resolution by 1.5 down to ultra performance, where we lower the resolution by 3. Then, when we add in the rendering time of FSR3 in this case, which is around 1 millisecond, you can see that on all the quality settings, the render time is lower than the 16.6 milliseconds, and thus enabling us to run the game at 60 frames per second. Well, fantastic, but it does come at a cost. But before we talk about, well, the ins and outs of how an upscaler works, let's first talk about what type of upscalers are actually out there. Currently, there are 3 types of upscalers. You have spatial ones, temporal ones, and machine learning-based upscalers. Spatial ones, like FSR1, are a little bit boring. They require little integration work, and they don't actually do a whole lot more than the bilinear upsampling that I talked about already. They stretch out the pixels and maybe add a few sharpening tricks to increase the upscaled result. And as you can see, it's not really great. There's a lot of pixelation, And well, you can make it look a little bit better by adding in some temporal anti-aliasing, but it will, well, always stay quite pixelated and not really visually pleasing. What is more exciting are the temporal upscalers. But these do require quite a lot more integration work, as you need a color buffer, which is a visual representation of everything that is currently being rendered in your game, just before you add in post-processing effects. Then you need the depth buffer, which is a representation of everything that is being rendered and how far away it is from the main camera. Black, in this case, is really far away, like the skybox, and red is really close by the game camera. And lastly, we need the motion vector buffer. And again, this is a visual representation of how an object is moving, how fast it is moving, and in which direction it is moving. Then, every frame, we add a small patterned offset to the game camera. And then we capture the subpixel data over time and use this subpixel data to create a high-quality image by using very complex mathematics. For FSR3, for example, we have a dilation pass where we separate the forefront from the background. There's a disocclusion pass where we find all the pixels of objects that were occluded before in previous frames and are disoccluded in the current frame, or visible again in the current frame. We track changes in brightness, and we mark thin features such as wires and really tiny objects in the game. Then all of this data is used to weigh how much of the pixel data from previous frames should be used and be blended with the pixel data from the current frame to create a smooth, sharp, and detailed reconstruction of what a native frame should have looked like in the first place. Now you can imagine if we would use and blend all the subpixel data of all the previous frames with the current frame, the output would become really blurry and a lot of ghosting will occur. So all of these passes are actually used to minimize the use of the previous frame's subpixel data and primarily use the pixel data of the current frame. And then you get this as an output. On the left side, you can see the low resolution input, which is currently rendered at 360p and upscaled by FSR3 to 1080p. Which is quite impressive, actually, if you consider how little pixels are used on the left, considered to how many pixels are outputted on the right. And then there are machine learning-based upscalers. Now, these upscalers have the same basic requirements as the temporal upscalers, but not only have they all do they use all the complex mathematical passes, they also run the low-resolution input through a pre-trained inference model, further increasing the visual quality of the upscaled output. Some of the most well-known upscalers, machine learning-based upscalers, are DLSS, FSR4, XeSS, and PSSR for the PlayStation 5 Pro. And all of these machine learning upscalers make use of specialized hardware to speed up the calculations, because without this hardware, the machine learning-based upscalers would be slower than a temporal one, and well, you wouldn't get a lot of performance benefit from using them. So you really need to have this specialized hardware. And well, as you can see, this is DLSS being upscaled from 360p to 1080p again. And the upscaled results are even more impressive than when we were showcasing FSR3. DLSS 1 was the first of the machine learning-based upscalers, but it had to be pre-trained per game, which makes it quite difficult to integrate it, as you need a partnership with NVIDIA. And it had quite mixed results, a lot of blur, added blur and ghosting. DLSS 2 then later solved many of these issues, but it still had quite a lot of ghosting issues. And later iterations of DLSS 3 and now 4 are much more impressive, offering sharper and way more detailed results. And this is, by the way, upscaled by using DLSS 4.5. So now that we know a little bit more about upscalers and how they use, what are the downside and side effects of using an upscaler? Well, we already know spatial upscalers suck. For temporal and machine learning-based upscalers, it's a little bit more complex. One of the side effects of using a temporal upscaler is, well, using subpixel data over multiple frames and using them to blend into a high resolution upscaled output is a little bit the same as what temporal anti-aliasing also does without the downscaling part, which is both a positive and a negative point. Personally, I'm a big fan of temporal anti-aliasing. I really dislike jittering and shimmering pixels. I prefer to have a really stable output. But the public perception of temporal anti-aliasing is that it adds a lot of blur and ghosting effects. And this public perception also really transferred over from TAA to upscalers, which is quite a bummer. And another downside is that the depth and motion vector buffer that I talked about earlier are often lacking in certain information, which will result in looking something like this. This is supposed to be a tree, gently moving in the wind. But in this case, FSR3 is not getting any motion vector data from the motion vector buffer and will, well, just garble all the pixels and become hugely pixelated. And this happens a lot more in Unity than you'd think, as world space UI, GPU instance objects, terrain vegetation, and basically every transparent object in Unity isn't being added to the motion vector buffer. Which brings us to the challenges of integrating upscalers into Unity. Now, it isn't easy to integrate upscalers into any engine and to get the best visual results. It takes a lot of work, and bad examples really hurt the public perception, which is a shame because upscalers can enable you to, well, drastically lower the minimum required hardware for your game or allow you to insert fancy graphical features like real-time ray tracing. So when we start with the limited depth and motion vector buffer, luckily there is a solution for that, which is called the reactive mask, which is a custom mask where you can add objects into these masks, which tells the upscaler to use less of the data from previous frames and more of the current frame, cleaning up the upscaled results. And another big challenge in Unity is the use of multiple cameras. In the past, we've all been taught to use many cameras to fix a wide range of issues that you might have in a game with Unity. Like when you're building a first-person shooter and you don't want the hands and the gun to clip through a wall when it is actually clipping through a wall. One of the ways we've been taught to fix this is to add a secondary camera, have the first camera render the game environment, and the secondary camera only render the hands and the gun, and then you layer these cameras on top of each other. And then when the gun is clipping through the wall, it will still be rendered on top of it. The only issue here is that when you add two cameras on top of each other, the depth and the motion vector buffers aren't being merged correctly. And you can guess, it ends up with limited depth and motion vector buffers. Again, really creating a lot of artifacting in the output of the upscaler. Another side effect of using multiple cameras in Unity is that it adds a huge CPU bottleneck to the game, lowering performance. And, well, that brings us to the second challenge in Unity. It's very easy to get bottlenecked by the CPU in a Unity project. And upscalers really only give any performance benefit if you lower the rendering resolution of your game. But that is a way this gives more performance when you're bottlenecked by the GPU only. So before an upscaler becomes viable, you first need to fix all the CPU bottlenecks of your game. And lastly, one of the biggest challenges in Unity, is that Unity wasn't built to integrate upscalers in the first place. It took us many, many months to actually be able to prove that integrating an upscaler into Unity would work. And then when we decided to port the asset to a Unity Asset Store asset, it took us, again, many months to port it to URP and HDRP and to all the Unity versions out there. And Unity keeps changing all these versions to Unity 6, new render graph, for example. So we are really proud that we've been able to publish these assets on the Unity Asset Store. So should you use an upscaler? Yes, you should. But I might be a little bit biased because I sell these assets. So let's look at a real-world example instead. City of Springs again. Originally, the game ran great on an NVIDIA RTX 3060 at 4K, which is, well, I can imagine this is quite a high minimum required hardware for a small-time indie game production. And this is the reason why we decided we wanted to investigate time to see if upscalers were an option to increase the performance of the game. And we're really glad that we did, because after integrating FSR 2 back then, we were able to lower the minimum required hardware specifications to NVIDIA GTX 1050. And it also opened up the doors of porting the game to a previous generation of consoles, even the Switch 1, which was never our plan anyways. An added side effect of using upscalers, you can also run them at the native resolution of your game, not doing any downscaling at all, and thus adding the industry's best temporal anti-aliasing to your game and increasing the visual quality of the game. So should you use an upscaler in your project? I'd say yes, but you should always give the player the choice whether they want to use it or not. And by adding in the upscalers, you can increase your target audience by lowering the rendering of the minimum required hardware specifications of your game, or making it visually more pleasing by being able to add in fancy new graphical technologies. Which brings us to the common misconceptions about upscalers. Upscalers will make everything blurry. Well, since the beginning of 3D graphics, aliasing and anti-aliasing have been a thing. FXAA, SMAA, MSAA, TAA. Some are fast but blurry, others duplicate the frame time, another one is limited to specific rendering types only, and another one adds ghosting. There simply isn't a one-hit wonder solution anti-aliasing out there. But in practice, by adding a cheap CAS sharpening filter, you can get rid of all the added blur and ghosting introduced by temporal anti-aliasing or by upscalers. As you can see in this video, on the left, I hope you can see it well. On the left is Unity's standard temporal anti-aliasing, and on the right is the upscaled output of DLSS. And the upscaled output it's being rendered at 360p and upscaled to 1080p with a lot of zoom in on the specific pixels. And as you can see on the left one, there's quite a bit of jittering and it's very blurry. And on the right is, well, it's very detailed and rock steady. So I will start using DLSS and FSR 3 as native temporal anti-aliasing instead of any other option. Talking about DLSS, is DLSS actually always better than FSR? Well, yes, DLSS is considered to be the best-in-class upscaler, but only if your game works really well with the pre-trained inference models. I've seen quite a bit of a few customers who had visual artifacts when they were using the latest DLSS 4.5 new transformer models. And this is because stylized high-concept indie games often have a lot of clean, low-poly visuals, and for some reason the DLSS pre-trained models aren't really trained well for these types of games. In this scenario, FSR3 can actually be a better option for more deterministic visual quality. And additionally, DLSS is locked to NVIDIA GPUs only, while our FSR3 asset works on basically every platform out there without any hardware requirements. And only lazy developers use upscalers. Well, there's a public perception that upscalers are the fast hack to get the best, easy performance for your game instead of doing a lot of performance optimizations. Well, it takes a real effort to actually make an upscaler work well with your specific game. You need a lot of understanding of the performance of your game, do a lot of profiling to know its bottlenecks. Upscaling isn't a silver bullet magical solution imported and you have the best performance out there. No, you first need to do a lot of steps like CPU performance optimization before an upscaler actually becomes relevant. So, no, you're not lazy. So now that we know the ins and outs of upscalers, what about frame generation? Funnily enough, these technologies are often really close together, but that's mostly because of the marketing train and the hype train of AMD and NVIDIA, and the branding issue. But upscalers and frame generation are really different technologies, where upscalers take a low-resolution input and make it look like native high-resolution output. Frame generation actually takes two already rendered frames and creates a whole new frame right in between, effectively doubling the frame rate, allowing for much smoother gameplay, with the added side effect and downside of increased input lag. You can imagine that if you have to wait before two rendered frames are completely rendered before you can push them to the screen, you are lagging behind a few screens, and thus, having a later input. Luckily, we're also working for a new asset that is counterbalancing this input lag, but that's a talk for another time. Frame generation is really interesting for us because it doesn't really care whether you're bottlenecked by the CPU or the GPU. If you enable it, it just takes a load of both the CPU and the GPU, leaving more headroom and also making an upscaler more effective, which is even more interesting because if you use them together, there's some kind of compounding effect, making both of them more effective as well. Which is one of the reasons why my business partner, Nico, and I have been working very hard at creating an integration of frame generation for Unity as well, and we're really proud that we launched it last week. I've taken the liberty to make a short video and play it back at 10% speed to best showcase it. When frame generation is off, there's around 36 frames per second, and with frame generation on, it jumps up to 60. And in this scenario, there wasn't any real input latency that I could feel. So and this is not even the optimal scenario. So frame generation is really interesting and quite impressive. But of course, just as with all the upscalers, frame generation also has a cost. You can imagine that rendering a whole new frame right in between two already rendered frames also takes quite a bit of GPU time. But because frame generation does double the frame rate, you can still see a factor 1.5 to 1.8 performance boost when frame generation is enabled, which makes it, useful in a lot of scenarios. I can imagine this being a lot of information that I just dumped on you. So if you have any questions, you can scan the QR code for more information, or you can ask any question that you'd like right now, or if you, I don't know how much time we have, but we can also do it. You can ask them here on the floor. I'll be at INDIGO all day. Yeah, sure. One second. We're going to get a microphone for you. Thank you.
Thank you. What is your experience with upscaling on the Switch 1? Like what works and what doesn't?
It's a very difficult work to get an upscaler work on the Switch 1 really well because the GPU is, well, as you might know, not really
it's
powerful.
a phone from 2015.
It's really old, yeah. Well, the cost of running an upscaler on such a slow hardware is quite high. So in this case, the point where you gain performance rather than lose it is very easy to get. But City of Springs has been ported to the Switch 1 as well, and we used SGSR1, which is a spatial upscaler, so it's the less than desired upscaler. But it does increase the visual quality because the screen is so little, and for when you plug it in a TV, it's less visible as well because the TV has a different pixel type, so it works all right. For the Switch 2, maybe some of you already have access to the SDK of the Switch 2. I've been told that the Switch 2 has a really strong GPU, so a lot of upscalers will work better on that platform.
All right, thank you.
Thank you for the question.
We have time for one more question. Anybody? No? Cool, then I'll have one question. So
Sure.
let's say I'm a new tech person getting into Unity and all the graphical stuff. Any resources that you would recommend for me to get into this, to your skill set, so to say?
My documentation of my assets. No, well, we do have an extensive documentation, of course, of how to use upscalers and what the best way to use them is as well. But I've also have a YouTube channel where I talk about game development in general and what the best ways to get performance optimization tips and stuff like that. So if you Google me on YouTube, I'm sure you will find the YouTube channel. And there's lots of resources on game development in general, but also the upscalers.